Well, we're back here in the cave of science, and we're going to look at Newton's second law of motion here. Really, the second law of motion really is a formula, and this formula is force equals mass times acceleration. And you can see, of course, Newton's always, giving credit for the apple falling and, coming up with a lot of this. Well, let's look at the units of force here. And if we know mass, the standard unit is the kilogram. From acceleration, some of the standard problems we've looked at, it's meters per second squared. And if you multiply those things out, you'd have a kilogram meter per second squared, and that is called a capital N, which stands for Newton. And so when you see a capital N, that is a Newton, it's a kilogram meter per second squared. Well, if you look at this formula, force equals mass times acceleration, you can definitely see force is directly proportional to acceleration in mass. As mass increases, the force is going to increase. As acceleration increases, the force is going to increase. If you hold the other ones constant, so if we kept the mass constant and increase the acceleration, it's going to hit with more force without a doubt. And let's take a look at that. Now, let's say we got a bowling ball here, and this bowling ball has a mass. Well, for grins, let's just say it's 10 kilograms. And we're over at the bowling alley, Mr. Olson's PE class, and let's say we accelerate that bowling ball at 10 meters per second squared. Well, we can figure this out. So force equals mass times acceleration. The mass is 10 kilograms. And again, I like to put things in parentheses. Whatever works for you is fine. Acceleration is 10 meters per second squared. So if we do the math here, we have 100 kilogram meters per second squared, which equals 100 newtons. So as that bowling ball is flying down the alley and it gets up to the pins, it's going to strike the pins with a force of 100 newtons. Well, quite often you're going to see this formula written for terms of acceleration. So let's see if we can do that. Force equals mass times acceleration. And we want to get acceleration by itself. So we got to divide each side by mass. And if we do that, we see these two cancel out. So force over mass equals acceleration. And what this is saying here is acceleration and mass are inversely proportional. As the mass increases, keeping the force constant, this number becomes smaller, so acceleration is going to decrease. As the mass gets smaller, keeping this constant, we're going to find that the acceleration is going to increase. And what this is really saying is it's easier to accelerate or to move a smaller object. Let's think of Justin Verlander here. He takes a baseball, and let's say this baseball, just for instance, let's see if we can draw a baseball here. Say he throws it and it strikes the catcher's mitt with a force. Let's say it's 1,000 newtons. He can accelerate a baseball. Baseball probably is like 1.1 kilograms or less. He can accelerate that very, very quickly. If you take the force and divide it by the mass, you can see that's a pretty quick acceleration. Where if it was a bowling ball, he definitely could not accelerate it as quick. So when you start thinking about acceleration, always think of it in terms of mass. It's harder to accelerate larger objects. You see this, that's why rockets have such powerful thrust on them, because they need a lot of force to get them to go. Let's see what else. One other thing on here. There's always one constant acceleration, and that's the acceleration due to gravity. And I'm just going to bring that up. Acceleration due of gravity. gravity, or the force pulling downward, is always going to be, we're going to round it up to 10 meters per second squared. And that is a constant. Everything will accelerate downward or towards the center of gravity on Earth at 10 meters per second squared. Actually think about it, it's like 9.81 meters per second squared, but if you round it up to 10, that'll work for everything we're going to do. So kind of the keys here to remember is large objects are harder to accelerate. Large objects, hard to accelerate. Or think of the inverse, small objects are a lot easier. The other thing there you need to remember on this formula, and we'll keep coming back to this, is that force and acceleration are vector quantities. And remember, vector quantities have magnitude and direction. I'm not going to put these arrows in all the time. You'll see them in different things. But force and acceleration are vector quantities. Mass again is in kilograms. So we'll talk about this in class. I know you've got some questions on this on one of the worksheets, and we'll see you next time.